Next, I'm going to show you how to use differentials of any equation, implicit or explicit, in order to come up with something called the local linearization of the equation. And the local linearization is intimately related to the tangent line. Essentially, it is the tangent line. So we'll take a look at how to do this, but it's a little bit more general in the sense that it can apply to having more variables than just what you'd be limited to when finding the tangent line of an explicit equation. So suppose we have, some equation. So either y is equal to f of x, or r of x, y is equal to 0, or maybe even, a function of more than one variable. V is equal to f of r and h. So the volume of a cylinder is a function of both the radius and the height, something like that. So we're looking at something called local linearization, meaning that we have the value of the function at one specific point, and we're trying to see and approximate what the values are for nearby points in the domain. So local in the sense that we're only looking at nearby points. So this is only valid in a short regime centered about a particular point that we know the output value of. Linearization means that we use differentials, aka we use derivatives, to solve for an approximation. So we basically approximate the function as a linear function and then use linearization instead of, so basically we're ignoring all the nonlinear effects by just looking at the values of the derivatives at the particular point. So to do local linearization, you do the following. So you start with some equation. Start with an equation. So r of x, y is equal to 0. And without loss of generality, I'll say it's in this form because even y is equal to f of x, you can say, well, r of x, y is just y minus f of x, and it can be in the same form. So you start with some equation, and then you compute, or you take the differential. Take the differential. This leaves you with an equation of the form, m of x and y dx plus n of x and y dy is equal to 0. Basically, whenever you take the differential, you'll always have something times a dx plus something times a dy, so you're left with this. So that by itself is just the differential. If you want the implicit derivative of r, our equation, r of x, y equals 0, with respect to x, you just divide this by the dx. So we get this, whatever this is, something involving x's and y's, plus whatever this function is, times dy dx is equal to 0. So it's the same sort of deal. But in general, we can say it's some stuff times a dx plus some stuff times a dy. So that's all the m and n functions are. It's just stuff that depends on x and y. It's whatever you get when you compute the differential. So for example, if we have x to the 4th, y to the 7th equals 9, the differential is going to be, okay, derivative with respect to x, 4x cubed, y to the 7th, multiplied by the dx, product rule, so plus derivative with respect to y, 7x to the 4th, y to the 6th, dy equals 0. So here, m of x and y would just be the 4x cubed y7, and n of x and y would just be this stuff. In general, you always get something times a dx plus something times a dy, so there it is. So let's move that out of the way. Okay, so we take the differential. Now, to obtain the local linearization, replace each differential. This is slightly confusing. This is the differential of the entire equation, but it's kind of a nomenclature thing. But the differentials themselves are the dx and the dy. So dx is a differential, dy is a differential. So when you take the differential, basically that's just the way we say go from this equation to that equation. But the differentials themselves, when you refer to a differential as a noun, would just be dx or dy. So replace each differential with a corresponding finite difference. So in other words, example, dx is replaced with delta x. dy is replaced with delta y. So we obtain m of xy delta x plus n of xy delta y is equal to 0. So that is, this equation is called the local linearization. So what did we really do? Why are these equations different? Well, remember, differentials are viewed as infinitesimally small quantities. So they don't have any values whatsoever. They're as close to 0 as you want. The dx and dy, they're limited. Delta x, delta y are finite quantities. They actually have a size. So delta x might be 0.2. They're small quantities, but of finite size. Delta y might be 0.8. So one of your differentials is always, so you're going to have differentials for the single dependent variable and the differential of your independent variable, or in the case of the volume of a cylinder, you might have two independent variables. Both the radius and the height can vary independently, and the volume depends on both the radius and the height. So there's always one dependent variable. So this finite difference of the dependent variable, the local linearization is a map that tells you how delta y depends on all the other finite differences. So if I change x by this small amount, this is approximately how delta y behaves. So this is actually called the differential with the local linearization, except for one thing. The equality becomes an approximation, and replace the equals sign with an approximation sign. Because the delta y and the delta x represent the exact change in y and the exact change in x when you have a little variation. So if x changes by 0.3, the exact value of the change in delta y is delta y. But what the local linearization does is it approximates a change in the y variable by knowing what the change is in the x variable. So that's why basically when dx and dy are not infinitesimally small, this no longer holds up as an equality. It becomes an approximation. And it's valid as long as delta x is small enough. So let's do an example. Suppose we have y is equal to the square root of x. Okay, so the differential dy, derivative of square root of x, is 1 over 2 root x times dx. So this is the differential. The local linearization is delta y equals 1 over 2 square root of x. There I go again. It's approximately 1 over 2 root x times delta x. So this is the local linearization. So let's see how we can use this. Okay, so suppose we have a fixed point. So let's do 9. So I know the square root of 9. So let's look at exactly, x is equal to 9. And let's look at the local linearization about x is equal to 9. So the local linearization about x equals 9 is going to be given by delta y. Square root of 9 is 3. 1 over 2 times 3 is 1 over 6 times the delta x. What this means is y minus y naught is going to equal 1 over 6 times x minus x naught. Now the y naught is 3 because when I plug in 9 for x, I get 3. So delta y would be y minus 3, and that's equal to 1 over x times x minus x naught is 9, so x minus 9. So see, this is just the delta y, and this one is just the delta x. So, and it works if x is close to 9. So if you're doing a change in 0.1, so x is 9.1, so the delta x would be 0.1. So 9.1 minus 9 is 0.1, 0.1 over 6. And then, so square root, so y would be square root of 9.1, and these should all be approximately. Square root of 9.1 is approximately 3 plus 0.1 over 6. So that's the approximation of square root of 9.1 using local linearization.